Good morning. Today we're going over the first homework assignment for gases, and this covers primarily kinetic molecular theory of gases and individual gas laws. So this first section, we're just doing some simple conversions between pressure units because pressure is something that gases exert. And you see we've got a little chart here that looks at 1 atmosphere of pressure versus other pressure units, including millimeters of mercury and torr, which is the same as our millimeters of mercury, inches of mercury, pounds of pressure per square inch, and pascals. And these will be given to you on the test, so you don't need to worry about memorizing them. You just need to know how to use these conversion factors with dimensional analysis to convert from one thing to another. So primarily in this class, we're going to be using atmospheres and millimeters of mercury, also known as torr. But we can do all of these as long as they give us the conversion factors. That is not hard. So for this first question, they say let's convert 0.750 atmospheres of pressure to millimeters of mercury. And we look at the chart, we can see that 1 atmosphere is 760 millimeters of mercury. So we're going to put the millimeters of mercury on the top because that's what we want. That allows us to cancel the atmospheres. When we solve for millimeters of mercury, we get 570 millimeters mercury. Just plug that in. Perfect. All right, for part B, if they give us pounds per square inch and they want atmospheres, that's easy. We can start here with 33 pounds per square inch. Sometimes that's also referred to as PSI instead of this LB over inch squared. And we see here that 1 atmosphere is equal to 14.7 pounds per square inch. Atmospheres on top, since that's what we want, 14.7 pounds per square inch on the bottom, so those will cancel. And I get $2.24 atmospheres. Excellent. Next for part C, if they give us pascals, we can do that. We've got conversion factor for pascals in our chart over here. 1 atmosphere is 101,325 pascals. Just plug this in. That gets us to atmospheres. If I plug that in my calculator, 5.83 times 10 to the 8th pascals divided by 101,325 pascals in an atmosphere gives me 5754 atmospheres. And I can plug this in here. And oh wait, look at that. They want torr. That's what I get for not reading the question, but I'm glad that I saw the units they wanted. So now, because we don't have a conversion factor straight from pascals to atmospheres, straight from pascals to torr, but we do have from atmospheres to torr and from pascals to atmospheres, we can go through there, plug in 760 torr in 1 atmosphere. My atmospheres cancels, my pascals cancel. And multiply that by 760. Let's convert that to exponent notation. 4.37 times 10 to the 6th torr. There we are. Excellent. All right. This next problem is just more of the same, but it doesn't give you those conversion factors, but here they are. We still got them because we just did those. So this first question is asking to convert from millimeters of mercury to atmosphere. So we're going to use that same conversion factor, 760 in 1 atmosphere. Again, I'll give this to you on the exam, so you don't have to have them memorized. But starting with 440 millimeters of mercury, 760 millimeters of mercury in 1 atmosphere. Plug that in. Convert that back to normal notation. That gives me 0.579 atmospheres. Excellent. Now they want to know how many pascals that is. Here we've got a conversion between atmospheres and pascals. We can just tack that on to the same conversion we were doing at the beginning here. 1 atmosphere now goes on the bottom, so those will cancel. Already got that in there, so I just multiply that by 101,325. And that's 58,661 pascals. Except they only started with 3 significant digits, or actually 2 there. So probably just 59,000 would be sufficient. There we are. Next, these questions have to do with the theory behind gases, how they work. This is called the kinetic molecular theory. These tenets here, which are also in your book, are also in the lecture notes. You do need to know them. You do need to be able to explain kind of how gases work based on the kinetic molecular theory. So this one is looking at a gas in a sealed rigid container. They want to know what happens if you increase the temperature. Well, if I increase the temperature, if you look at this particular section, it says kinetic energy is directly related to temperature. So if I increase the temperature, I can expect the kinetic energy is going to go up. So I can answer that one for sure. And then because the kinetic energy goes up, then we know that the energy of individual particles increases. That means the collision force that they exert increases, and pressure is collisions, essentially. And so because my energy increases, then I know that my pressure is going to increase as a result of the fact that the collision force increases. That's the collision of gas particles are elastic. So we can also select the collision force of the gas particles increases. Those 3 for sure. And then looking at these other ones, the volume, let's see, the number of gas particles, that doesn't change. The speed, yeah, that'll go up because the kinetic energy, which is movement, increases, but the volume doesn't because I'm in a rigid container. That's what rigid means. The sides can't move. So that's what we've got for part A. And for part B, another gas in a sealed rigid container, but I'm adding additional gas particles this time, not changing the temperature. So what will happen? Well, in the first place, yes, the number of gas particles increases because I added gas. And collision frequency, that's going to increase too because now I have more particles in a smaller or the same area. So it's more concentrated. They're going to bump into each other a little more often. Kinetic energy does not change because the temperature does not change. Kinetic energy directly proportional to the temperature. So that won't change. The volume of the individual particles does not change. The space between them might change, but the particles themselves, they don't change volume. Speed of the gas particles does not change because the kinetic energy and temperature stay the same. And finally, we can guess that the pressure of the gas will change because, again, pressure is collisions, and the collision frequency is going to increase as I increase the concentration of the gas. So that's that particular problem. You can expect a problem like that on the test. Next, this question asks us about assumption of the kinetic molecular theory and how it explains that a balloon is going to collapse if I basically make it very cold. And so if the temperature goes down, they're saying the volume goes down too. So why would that be? Well, it's saying velocity of gas molecules is proportional to the Kelvin temperature. So if I lower the temperature, then their speed goes down. If their speed goes down, then they're not colliding with the walls of that balloon as often or as energetically. So the pressure goes down. So the internal pressure goes down, then the external pressure causes the balloon to collapse. So that is exactly what we're looking at here. These other ones don't really have anything to do with the temperature, which is what's happening here. So you've got a temperature change. Here I've got a sample of ideal gas, and here I've got Boyle's law, which is explaining to me the pressure-temperature relationship, which could be described with kinetic molecular theory, but here we're going to look at it mathematically. Boyle's law, initial pressure times initial volume equals final pressure times final volume. So I can literally just plug this in. I have initial volume, initial pressure, final pressure, and now I want final volume. So here's my formula. And I highly recommend solving for the thing you want before you plug stuff in. So I'm going to divide both sides by P2 in order to solve for V2. This is just algebra. And I see that V2 is equal to P1 V1 over P2, which is the same as saying P1, which was initial pressure, 312 torr, V1, initial volume, 38 liters, P2, final pressure, 1560 torr. And notice that even though I'm doing algebra with a predetermined formula, I'm still including my units, okay? Because dimensional analysis says, look, you should always include your units. It'll help you understand what's going on. And you can see here, torr divides by torr. I'm left with liters, which is a unit of volume. That's what I was solving for, was volume. So I know I did it right. I know I put everything in the right place. And now I can plug it in. Because the units cancel, it doesn't matter whether your pressure is in torr or in atmospheres or in any other unit, so long as you have the same units on top and bottom to let them cancel. Same thing is true of the volume. Doesn't matter if you're talking about liters or millimeters or milliliters or whatever, so long as you're consistent. Watching the unit, they'll tell you what units you'll get. Should be 7.6 liters. Okay. Same story. If the volume of the original sample in part A has this initial pressure, changes to 68 liters, what would the change in pressure be? What would the new pressure be? Now here we're solving for P2 instead of V2. So P1 V1 equals P2 V2. I divide both sides by V2 so that those cancel, and that will solve for P2. Now let me just plug that in. P1, 312 torr. V1, 38 liters. And V2, 68 liters. Liters cancel. I'm left with torr. That's the units they want, so I know I did it right. 312 times 38 divided by 68 gives me 174 torr. Just like that. Okay. All right, this is the same problem, same type of problem. They give you a volume, they give you a pressure, and then they change the pressure. They want to know what the new volume is. So I know, because I'm looking at just units of pressure and volume, I've got to use Boyle's law. P1 V1 equals P2 V2. And I'm solving for V2, so I divide both sides by P2. V2 is P1, which is pressure 1. 5.2 atmospheres was my original, times my original volume, in this case 350 milliliters, divided by my final pressure, which in this case is 1 atmosphere. My atmospheres cancel. If I plug this into my calculator, 5.2 atmospheres times 350 milliliters divided by 1 atmosphere gives me 1820 milliliters. Those are the units they left me with here. Oh, but they want liters. Okay, so by watching my units, I can see they want another conversion here. We remember that 1820 milliliters, we've got 1 liter is 1,000 milliliters, so we can do that conversion. We know how to do metric conversions. 1.82 liters. Alternatively, you could have converted milliliters to liters at the beginning, and said instead of 350 milliliters, you could have said, oh, I know they want liters, so I'll just convert that to 0.350 liters. And then when you solved for that one, you would have had it in liters. Either way is perfectly appropriate. Next, again, if I've got volume and pressure and I change the volume, what will the new pressure be? I'm going to plug this in. This time again, we're looking for P2, because we're looking for the new pressure. P1 V1 equals P2 V2. Divide both sides by V2. Now we're solving for P2. So P1 was 380 millimeters mercury. V1, initial volume was 400 milliliters. V2, it is expanded to, so that is the final volume. Make sure that you don't mix up which one is the initial and which one is the final. And if I plug that in, 380 times 400 divided by 800, I get a new pressure of 190 millimeters of mercury. For all of these problems, they're going to say there's no change in temperature because this relationship is only valid with no change in temperature, which is why they will specify that to make sure that you are aware that those are the conditions that under which this is occurring. All right, so what happens if we change the pressure, or what happens if we change the temperature? Well, we did talk about how that increases the frequency of the collisions, it increases the energy of the collisions, and so your pressure goes up. And so we get this formula here, P1 over T1 equals P2 over T2. This is Gay-Lussac's law. You don't necessarily have to memorize these. I will not give them to you. But later on, we're going to discover a complete law that covers all of these, and you can deduce these individual laws from that. So if you can see how to derive these laws, then you don't have to memorize them because I'll give you the other. But if you can't see how to derive them, you might just want to memorize them. It's up to you what you prefer. But these problems then are solving for either pressure or temperature. And again, we're using algebra to solve. So if I'm looking for P2, then I've got to multiply both sides by T2 so that those will cancel. So P2 is equal to the final temperature times the initial pressure divided by the initial temperature. So my initial pressure is at 605 torr. And again, I could use torr or atmospheres or PSI, whatever I want for pressure, so long as those are the units that I use for both, and that's what they want for P2, so that will work. The initial temperature is 13 degrees Celsius. Uh-oh, I'm gonna have a problem here. I cannot use Celsius for temperature. I could use anything I want for pressure, but for temperature, I have to use Kelvin. The reason is that Celsius can be 0 and I cannot divide by 0. So I have to use Kelvin. All right, so remember that Kelvin equals Celsius plus 273.15. And I will give that to you. You don't even have to memorize that, okay? But we do have to do that conversion. So if the initial temperature is 13 Celsius, then the initial temperature is 13 plus 273.15. It's 286.15 K. Let's plug that in. It's the initial, so that goes on bottom. And the final temperature here is 99 degrees Celsius, which is 372.15 K. My Kelvins cancel, and I'm left with torr, which is what they wanted. So 372.15 times 605 divided by 286.15 gives me a new pressure, 787 torr. Next, same story, but now I'm solving for T2. This is a little bit trickier. P1 over T1 equals P2 over T2. I have to get T2 by itself, but I also have to get it on top. It is not okay that it's on the bottom. So what I'm going to do is multiply both sides by T2. That gets it on top. And then I also have to multiply both sides by T1 over P2 so that I can get this stuff out of the way so it's by itself. So rearranged, this comes out to be T2 equals P2 times T1 over, T1 over P1. This P2 is already here. T1 over P1. So my final temperature is the final pressure multiplied by the initial temperature divided by the initial pressure, which in this case, we've got the same sample. So they're saying the pressure is changed to 6050. That's P2. Torr. And my initial temperature was 13 degrees Celsius, which we said was 286.15 K. And my initial pressure was 605 torr. So the torrs cancel. I'll be left with Kelvin. They want Celsius, but let's take this first step at a time. So we have 6050 multiplied by 286.15 divided by 605. Now that's in Kelvin. So now I'm going to say Kelvin minus 273.15 gives me the Celsius temperature. So that is 2,588 Celsius. Okay. Next, glass laboratory flask filled with gas at 24 Celsius, 1 atmosphere of pressure, heat sealed and heated. So again, we have P1 over T1 equals P2 over T2. And they're solving for final pressure. So let's multiply both sides by T2. That'll give us P2. All right, so the final pressure, or the final temperature was 91 plus 273.15. That's going to make it Kelvin. And the initial pressure, 1.02 atmospheres. This will be Kelvin. And the initial temperature was 24 degrees Celsius. Again, that's going to convert the Celsius to Kelvin, so our Kelvins will cancel. I'm just going to use parentheses to do this all in one go. 273.15 plus 91 times 1.02 atmospheres. Divide that by 24 plus 273.15. Gives me a final pressure of 1.25 atmospheres. Oh. They gave you 2 digits, so they probably just want 2 digits. It's possible they want me to round up to 1.3. Oh, okay. Well, that's close. Close enough. There we go. Next, how will the volume of a fixed sample of gas change if the pressure is doubled and the temperature is doubled? Well, according to our equation here, P1 over T1 equals P2 over T2. If the pressure is doubled and the temperature is doubled, how would the volume change? Well, we want to know for volume. P1 V1 equals P2 V2. If the pressure is doubled and the temperature is doubled, first off, it's important for us to understand that when they're saying the pressure is doubled, they're not talking about the pressure on the inside of the gas, the pressure on the outside that is affecting the gas. So if we're looking at something like a balloon whose volume can change, if we increase the temperature here, but we increase the pressure here, that's what it's saying. Increasing the temperature here would also increase the pressure correspondingly. The pressure would go up. So pressure goes up. But if the pressure goes up out here, then with the increased collisions, those will be offset by the increased collisions from the outside. Essentially, you double what's on the inside, you double what's on the outside, and there should be no change. A little hard to see. All right, next, Charles's law is talking about the relationship between volume and temperature. So for this one, we've got the formula V1 over T1 equals V2 over T2. Very similar to the one we just did. And again, temperature will need to be in Kelvin. Volume can be in anything so long as your units are conserved. Here they're solving for V2, so multiply both sides by T2. That gives us V2. So T2, final temperature. Temperature changes to 84 degrees Celsius. That'll convert it to Kelvin. Times V1, initial volume of 1680 liters, divided by final temperature, initial temperature, which was 42 degrees Celsius. Convert that to Kelvin. Our Kelvins cancel, and I'll have my answer in liters. Gives me a new volume of 1904. There we go. Now this time they want to solve for T2. Again, it's a little tricky because T2 is on the bottom. So I want T2 on the top and by itself. So I'm going to multiply both sides by T2 so that I can get it on the top on this side. And then to get it by itself, I'm going to multiply both sides by T1 over V1. So that my T1s will cancel from the left-hand side, and so will the V1s. And that leaves me with T2 is equal to V2 times T1 over V1. The second volume, they say, is 3360 liters. The initial temperature, again, is 42 Celsius, so we've got to convert that to Kelvin. See if I can get myself more space. And divided by my initial volume, which again was 1680 liters. Liters cancel. 3360 times 42 plus 273.15. That makes it Kelvin. Divide that by 1680. Gives me 630.3 Kelvin, but they want Celsius, so now we have to subtract 273.15 to get 357 Celsius. Okay. Note that I'm always including the whole number, 273.15, even though I know I'm going to round at the end. But it's always best to include as many digits as possible until you get to the end, and that's when you round it. So this next problem is also Charles's Law problem, looking at a hot air balloon. And they give us the initial volume and the initial temperature, and they want to know the final temperature if we're given the final volume. So again, V1 over T1 equals V2 over T2. They're looking for the final temperature. So we did rearrange that, and we determined that T2 is V2 times T1 over V1. It's just algebra. So final volume that they want, 1,300 liters. And initial temperature is 14 degrees Celsius. Have to convert that to Kelvin. And initial volume, 990 liters. Should be 377 Kelvin, which is 104 degrees Celsius. Oh, very close. Careful with the rounding. They only want 2 significant digits, so that's just 100. Again, I don't test you on significant digits, so. All right, elastic container, that means the volume can change. Occupies this much volume at this temperature. What would the volume be at the new temperature? So again, same story. V1 over T1 equals V2 over T2. And here they're looking for the final volume. So we'll multiply both sides by T2. That solves for V2. So initial volume, 148 liters. Initial temperature goes on the bottom, 85 degrees Celsius plus, got to make that a Kelvin, and the final temperature, 15 degrees Celsius. So our Kelvins will cancel, we'll be left with liters, and those are the units they want. Always a good idea to triple check. 148 liters, multiply that by, that is 15. Divide that by 119 liters, right there. All right, volume and moles. More particles, takes up more space. So we get this relationship between volume and number of moles. Direct correlation. And we can plug these in here. Got initial volume divided by the initial number of moles equals the final volume divided by the final number of moles. We've got the cylinder, constant pressure. We have 2.2 moles of gas, that's N1 at this initial volume. If I lose this much gas, then what would the final volume be? All right, looking for final volume, that's V2. So we're going to multiply both sides by N2. So that cancels, we'll solve for V2. So V1 is 49 liters. N1, initial number of moles, is 2.2 moles. And they said 0.6 moles leak out. So my final moles is going to be the initial 2.2 minus the 0.6 that leaked out. Okay. I could calculate that before I put that in, but it's easy to just put that in. 2.2 minus 0.6. That's my final number of moles. So multiply that by 49 liters. Divide that by the initial 2.2 moles. And now I'm going to only take up 36 liters. Next, same equation, sample of gas has initial volume of 62 liters here. Determine it contains 1.8 moles of gas, so V1 equals 62 liters, N1 equals 1.8 moles. The next day you notice that some of the gas is leaked out, but you don't know how much. The new volume is 15.5 liters, so what is the new number of moles? So same equation. Now looking for N2, so I'm going to multiply both sides by N2 to get it on top. And then I have to multiply both sides by N1 over V1 to cancel those. So I get N2 is equal to V2 times N1 over V1. So plug these values in. We had 15.5 liters for V2, 1.8 moles per N1, and 62 liters for V1. And it looks like I have 0.45 moles left. Next, how many moles of methane gas are in this size of a storage tank at STP? This question refers to Avogadro's law, which says that yes, volume and number of moles are directly correlated, and not only that, we can say that at STP, which is standard temperature and pressure, temperature 0 degrees Celsius, pressure of 1 atmosphere, just to give us a baseline, at STP, 1 mole of any gas occupies 22.4 liters. So this becomes a conversion factor we can use at STP to convert between volume and number of moles. So if I've got methane gas and I have 1 times 10 to the 5th liters of it, and I know that every 22.4 liters contains 1 mole because I am at STP, I can calculate the number of moles there. So 1 times 10 to the 5th, divide that by 22.4, and I get 4460 moles. Now how many grams is this? Ooh, now we're going to put together with what we know about moles, with what we know about gram to mole relationships. CH4 has 1 carbon at 12.01 grams per mole. That's from the periodic table. You don't have to memorize it. 4 hydrogens, each at 1.008 grams per mole, again from the periodic table. So CH4 has a total mass of 16.042 grams per mole. So I'm just going to add this in to my dimensional analysis. Okay, so moles cancels and I am left with grams. So 1 times 10 to the 5th divided by 22.4 liters in a mole multiplied by 16.042 grams in a mole, and let's round that to 7.16 times 10 to the 4th grams. Okay, so ever so slightly off between what they said and what we got. Likely has to do with the number of digits that we keep from the periodic table. Depends on which periodic table you use. If you use the one that I give you on the test, then you'll be fine on the test, so don't worry about that. Next, how many grams of carbon dioxide gas could the same tank hold? The key here is to remember that all gases behave the same. So If I'm holding this many moles of CH4, I'm holding this many moles of CO2, and the only difference is this. That's the only thing that changes. Everything else is the same because all gases behave the same. So here I'm talking specifically about CH4. Here I can talk specifically about CO2. It's the same story. Except that now CO2 has 1 carbon and 2 oxygens for a total mass of 44 grams per mole. So 44.01 grams CO2, 1 mole of CO2, moles cancel. We see 1 times 10 to the 5th divided by 22.4 liters in a mole. Multiplied that by 44.01 grams in a mole, and that's going to hold a lot more. That's going to hold 1.96 times 10 to the 5th. Grams of carbon dioxide. All right. Which sample contains more molecules, 1 liter of oxygen or 1 liter of hydrogen at STP? Well, it's important to remember that hydrogen atoms are smaller than oxygen atoms. So hydrogen molecules are smaller than oxygen molecules. However, when it comes to gases, remember the size of the molecule itself is pretty much meaningless because there's so much empty space between them. What we need to remember is that volume is directly related to number of moles. So if I have the same volume, then I have the same number of moles. Which is kind of wild considering how much bigger oxygen is than hydrogen. But it's the same concept we just illustrated here. They contain, whether it's CH4 or CO2, even though this weighs 3 times as much, I'm holding the same amount. Okay. Which sample has the larger mass? Well, the oxygen, because they have the same number of moles, but oxygen weighs more. So it will be more dense. Next, consider a sample of helium and a sample of neon, both at 30 degrees Celsius and 1.5 atmospheres. Both samples have a volume of 5 liters. Which statement is not true? Let's see. Each sample contains the same number of moles of gas. That is true because they are under the same conditions and they have the same volume. Volume is directly related to moles. Yes. The density of neon is greater than the density of the helium. That is true because neon has a higher mass. So since density is mass over volume, then since the volume is the same, the higher mass means that neon would have higher density. They weigh the same amount? Nope, they don't. Just as we saw in this example, even though there's the same number of moles of CH4 and CO2, they're going to weigh different amounts because the individual molecules weigh different amounts. And each sample contains the same number of atoms. That's the same as the same number of moles. Of course they do, because moles is directly related to liters. So this is the one that is not true. Okay, that's it for this homework. I hope that was helpful. Have a great day.